Hi friends, welcome to Mechanical Explorations. On this part we are going to see about the effect of temperature on thermal conductivity. Moving on, see in solids it is arrangement and you can see there is a free electron, which means it is a metal. Like I have simply given the Q conduction equal to Q lattice vibration plus free electron. Same thing, whatever the Q conduction is, the thermal conductivity will also be there. So K equal to K lattice vibration plus K free electron. This is a very basic thing. And now coming to non-metals, how the thermal conductivity will be there in non-metals. With this definition, you can come to the conclusion is that when you increase the temperature, lattice vibration will increase. Yes, lattice vibration will increase, right? Heat conduction also increase. Whenever vibration increases, heat conduction will be increased. So what is the conclusion is, in case of non-metal with increase in temperature, thermal conductivity is increasing. This is a very general term. Now moving on to metal, what happen when you are increasing the temperature? Lattice vibration will increase, same thing in such a manner for non-metals. What happens? It will start to disturb the path of free electrons. You can see this dot 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 dot, these things are path of free electron. In case of metals, it has free electrons, right? When temperature is increased, lattice vibration is also increasing, but the path of free electron is getting disturbed. This is a thing which makes the thermal conductivity to decrease. Whatever I have given, you can see. So when free electron is getting disturbed, electron movement gets disturbed. That's the thing. And heat conduction decreases. Heat conduction decrease. When heat conduction decrease, due to this reason, in metals, if you increase the temperature also, thermal conductivity decreases. This is one basic term. These two things in non-metals and metals, you can take this for a ESE. See, for example, here it is given thermal conductivity of copper at 20 Kelvin is 2000 watts per meter square Kelvin. Whereas same thermal conductivity of copper at 20 degrees Celsius is just 400. You can see that when it is below the room temperature, it is 20,000 watt per meter square Kelvin. But when it is above the room temperature, that is below 100 Kelvin, when it is 20 degrees Celsius, that is more than 100 Kelvin, you can see that is just 400, which is 50 times more. From this, you can come to a conclusion is that at 20 Kelvin, copper acts like a superconductor. Yes, because 20,000 watt, 50 times more than 20 degrees Celsius. Now, in case of metals, the relationship between thermal conductivity and electrical conductivity is Weizmann's Franz law, and the ratio of thermal conductivity to electric conductivity is Lorentz number. These things are just for ESE 1 marks. There is no concept in this. See, now coming to alloy, what the thing is that you already know, regardless of metals or non-metals, alloy is a combination of foreign elements. There will be a structure like if gold is there, the copper is being adulterated. So it is a combination of foreign metals. So what happens in the alloy? What is the thermal conductivities? So foreign elements, what they will do? They will disturb the heat flow. So in general, because we need standardize, we are not going to do any research in our subject. We are going to prepare for GATE or ESE. So in general, alloy or heat treatment object have low value of K compared to pure metals. This is the thing we have to take. And now coming to non-metallic crystal structure, we have been giving a final conclusion. So you don't worry. Whatever we are going to do is based on 1 marks. Next, that's why I'm moving much faster. See, now non-metallic crystalline structure, the material like diamond, graphite, beryllium, oxide have high value of K because of pure crystalline order structures. See, now what the important thing among this is that diamond is having high value of K among the all known material at room temperature. Very, very important is diamond is the only non-metallic crystalline structure which can conduct heat but not electricity. I have given here conducts only heat and not electricity. See, that's why diamond is used in space applications for making satellites and all those things, because if there is anything goes wrong, there will be a very much loss. Our cost is very high, so that only diamond is being used there. It can conduct only heat, but it can't conduct like electricity, so the damage is very less. So we are used to diamond. That's why we are using diamond in space application. You can take this as a good quality 1 mark. And good conductor of electricity metals is good conductor of heat, but good conductor of heat need not to be good conductor of electricity. See, the vice versa is not possible. Heat to electricity is okay, electricity to heat it can't be there, like that they are telling. So why they are telling? Because they have one solid reason. Diamond is there, it has only conducting heat, not electricity. So material like asbestos, glass, wool and some porous materials are having low value of K, they are referred to as insulator. You can take this also thing. See, this is the overall thing. Whatever we have discussed, the conclusion is this. Thermal conductivity of non-metallic crystal structure is more than pure metal or like non-metal insulator. Similarly, pure metals thermal conductivity is more than this. Alloy is more than this too. Non-metal is more than insulator. In insulator, you already know, very less. Now moving on to fluid, to determine the thermal conductivity, it's very difficult because fluids you already know, that is random movement of fluid molecules, very much it will be not like in a structural or rigid position, structural arrangement like whatever we have seen in solids, that is metal and non-metals. So it is very difficult. What we have to do is we need to balance some standard equation to determine the thermal conductivity of fluids. For that we have seen that Bridgman equation. See what Bridgman has said, that temperature of liquid increases when density decreases. When density decreases, temperature is increasing. This is the thing that Bridgman said. You can take this equation, K liquid equal to AC rho 4 by 3 m power 1 by 3. This is an experimental result which we have get. So you can see the A is constant, C is specific heat, rho is density, m is molecular weight. I'm moving much fast because this all things are 1 marks. And kinetic theory, that is K liquid equal to mu C, and K of gas is 1 by 3 Vc. This is lambda density. So here V is termed to be root of 3 GT by m. These things are used in problems. This is a formula, you just need to memorize, no other way. And mu is termed to be dynamic viscosity, V is molecular weight, and G is the gas constant. Whatever the things we are using here, I have given all those explanation. See here lambda, what is lambda? Is mean free path, that is average distance between two molecules before collision. See, if you are considering atom arrangement, there will be lot of metals, lot of molecules. The distance between two molecules, one molecule is here, another molecule is here, means the distance between two molecules before collision, that is termed to be lambda, and it is termed to be the mean free path. So this is the one thing. So what kinetic theory tells you is that if you increase the temperature, kinetic viscosity is decreasing. That is the simple thing. What Bridgman said, temperature of liquid increases, density decrease. Here same, kinetic viscosity decrease if you increase the temperature, that's all. Now you can see that I have given that the thermal conductivity of liquid decreases with increase in temperature. Reason may be density or viscosity. For density, Bridgman equation. For if it decreases in viscosity, then it is kinetic equation. So in gases with increase in temperature, density decreases, lambda increase. This is all a general term. We need general term. We are not going to do any research. We need only general terms. So in gases, increase in temperature, density decrease, and mean free path, it is been increasing. See, gases, you already know the distance between one molecule to another molecule is increases. That's why mean free path lambda is increasing. Everything I have written, I have been explaining, so you can clearly watch what are the things. See, product of lambda and density remains constant. With increase in temperature, molecular velocity increases, collision rate increases, heat exchange increases. Same, there is nothing but everything is given. Like if you increase temperature, what happens? The velocity will be increasing. Velocity increasing, velocity is nothing but temperature. Same, velocity, temperature, velocity, both vice versa, same only. Like collision rate will increase. Next, there will be more heat transfer, that is heat exchange is increasing. Simply in case of gas, with increase in temperature, thermal conductivity increases and density decreases. Same things. The gas like hydrogen and helium has high value of K compared to other gases because of lower molecular weight. You have to take this for ESE 1 marks, all those things. Liquid mercury, liquid sodium, etc. high value of K compared to other liquids. So the liquid metals is widely used in power plant industry. That's why liquid metals are used in power plant industry. I think so. You are coming to know the concept why these things are used in power plants. So this is for fluids. What they are telling, the liquid metal is more thermal conductivity than liquid than gas. In general, whatever we have seen in general, we are going to say about solid, liquid, gas, right? Solid has more thermal conductivity than liquid than gas. See, I have just given for water thermal conductivity is 0.6 watt per meter Kelvin. Same thing, the air it is 0.023 watt meter Kelvin. See, I have just given to remember at least for water and air. It behaves like a insulator. And now coming to the term specific heat. Can see it's a quantity of energy required for unit mass to change the temperature by 1 degree or 1 Kelvin or 1 degree Celsius. See, first we address this thing, then we'll go to the definition. You can see this is the first law of thermodynamics for a closed material. You can see dq equal to du plus tw, and you already know W can be written as VdP, that is PdV plus VdP, and you also know that we can write these things, right? It's a differentiable term only, PdV plus VdP. And same thing, you can take ds common, you will get U plus PV. And here one important thing, how that Molière got this value of H. That is, here only he termed that this U and PV are termed to be enthalpy. Enthalpy we'll be seeing later, all those things. Initially I want to tell that here dq equal to dh. Here H equal to U plus PV. This H is equal to term to be enthalpy, and this is term to be internal energy, and this is work done. It comes from here. Similarly, if you divide it with mass, it will be specific. That's why I have written here all small letters. Capital letters, capital H equal to capital U plus capital P plus capital V divided by M. Then only it will come to specific. Now it is specific enthalpy, where you divided by mass. Now, same, that heat is directly proportional to mass. Simply our body, how much we are consuming, like how much mass we have, like same thing, this Q is directly proportional to M. Same Q directly proportional to temperature difference also. Only when there is temperature difference, there will be more heat conduction. This is the thing we have been seeing from the beginning. And you can also see Q directly proportional to M del T. And another thing, if you want to remove this proportionality, you have to introduce one constant, that is C. See, we are rearranging these terms only. Q equal to MC del T. Now, when it comes to the specific, you can see that this you are rearranging, that is Cp equal to 1 by M dou Q by dou T. Here pressure is constant. And you also already know that dq equal to dh, so I have substituted instead of Q, H. Pressure is constant, same thing. Now, what I have done here, you can see Cp equal to dou H by T. See, where does this M's gone? Nothing. Specific heat. I already said capital H divided by M is specific heat. So, we got this dou H by dou T, that is small h. Now, coming to when this specific thing which we introduce as a constant, when it comes to volume term, same thing, we will be getting dou Q by dou T, volume is constant. See, I want to tell one thing, we already know dq equal to dh. You substitute dq, here you substitute h. Now, in terms of h, what happens? It is U plus PV, but I have written only U, not PV. Because in volume, if volume is constant, boundary layer is fixed. If boundary layer is fixed, work done is 0. If work done is 0, this entire thing won't come. Simply we will get H equal to U. That is dq will be replaced by dh, and the H will be replaced by only U. Cv equal to 1 by M dou U by dou T. Volume is constant. Similarly, this is capital U divided by mass. We will be getting specific internal energy, that is small u. Hope so. This derivation, how the Cp and Cv we are deriving. Simply I can't tell like Cp and Cv. how we are deriving from this equation. I just want to give you. Now coming to the concept, what a specific heat is. See, imagine, you have to imagine one thing. Simply you imagine a wooden box. Here the atomic arrangement is fixed. So by external force, you cannot change the spacing between the two molecules. And the wooden box, right, you cannot compress also. It is incompressible. Only in gas we can compress. So in case of solids and incompressible, we can write that Cp equal to dH by dt or Cv equal to du by dt, both are same. See how these things both are same. Now in special cases, solid and incompressible fluid, Cp and Cv equal to same, that is constant. See, Cp is given as 1 by m dou h by dou t, and we have derived as dou h by dou t, dou u by dou t as Cv. When comes to solid and incompressible fluid, volume does not changes. So volume is same only. Hence for both the thing, constant pressure also you can take as constant volume. Both the thing Cp and Cv are equal to same only. Now I want you to understand very detailedly about specific heat. I will be giving you example. Please consider this as an example, that is I have taken here iron, that is Fe, and here there is air. See, iron also having mass of 1 kg, temperature 20 Kelvin, same as air. And you can see that you want to change this 20 Kelvin as 21 Kelvin. So what will happen, you will be supplying some energy. See, you supply some energy by 0.1 kilojoule, and you will see there is nothing is changing, the temperature is not changing. When you supply 0.1 kilojoule, the temperature is 20 only. Here also says same. It may be 20.01, but it is not going to change to 21. See, if you supply 0.1 kilojoule, it is not changing by 1 Kelvin. That is, this thing is not changing by 1 Kelvin. Here also not changing by 1 Kelvin. And when you supply 0.45, please be very careful, 0.45, sorry I can't write this here, 0.45 kilojoule, only the iron will be changed the temperature to 21 Kelvin. See, same thing in air also. When you supply an energy 1.005 kilojoule only, the temperature will be changed to 21 Kelvin. And when you consider water, now take water, same mass 1 kg and temperature 20 Kelvin. When you take this, in water what happens, if you supply energy of 1 kilojoule, the temperature won't change to 21. Same thing, 2 kilojoule, 3 kilojoule, 4 kilojoule, it never changes. When you supply energy of 4.18 kilojoule, it will change the temperature to 21 degrees Celsius. This is the main thing. We are taking in consideration that Cp of air is 1.005, because then only the temperature is be changed to 21. Same thing in water also. When we supply 4.18 kilojoule only, the temperature will be changed to 1 Kelvin. That is the main thing we have to consider. And this is termed to be the specific heat. That is how much amount of energy does this water, air or iron is observing in order to change the temperature to 1 Kelvin. That is termed to be specific heat. You will be see here. You can see it is a quantity of energy required for a unit mass to change the temperature by 1 Kelvin. This 1 Kelvin only I am been talking there. Now I hope so you understand completely what is specific heat is. When water is changing the temperature by 1 Kelvin at 4.18 kilojoule, what it means, up to 4.17 kilojoule the water has the capacity to absorb the energy. Only when it is changing the energy, that is the point, the Cp value which is 4.18 kilojoule is termed to be specific heat, Cp or Cv, because in fluid water, right, it is incompressible. Cp and Cv are same. Now here the things, C of water 4.18 kilojoule, and specific heat is a property of a medium. It's a very important thing. It's a property. It's able to absorb and store energy. Now we have also discussed about ion rate. Here I have said 0.45 to change, that is 0.45 kilojoule per kg Kelvin. So it is able to change the temperature by 1 degree Celsius. It means water can absorb 10 times more energy than iron. What happens? I have given that liquid is a good medium for storing energy. Now you have to understand another important concept, that is thermal diffusivity. See, I have given that the ratio of ability of a medium to conduct heat to the ability of the medium to store the heat, that is conduct the heat, ability of the medium to conduct the heat is K. To the ability, divided by ability of the medium to store it is rho C. We have been expressing this thing as like that. We know K equal to joules per second meter Kelvin. The K value, that is watt per meter Kelvin. If you take the watt in joules per second, you will derive the equation like this. And rho C, if you are writing the terms in term rho C, you will be taking meter cube Kelvin divided by joule. When you take this term, you will have the thermal diffusivity, that is, here I expressed this thing as A meter square by second. Now the thermal diffusivity alpha is purely dependent on property of medium. We will be seeing this through an example, then only you can understand clearly. Now coming to the example, please consider this as one body and this is another body where the area is same. I have given the area same, but the material is different material. See, if someone gives like you and is telling that you want to change the temperature, what is the main thing you have to say? You have to depend on two criteria only. That is, one criteria is thermal conductivity K and the other criteria is rho C. Only if you want to increase the temperature, what you should do? You should increase the value of rho C. And if thermal conductivity is increasing, this value will be decreasing because its thermal conductivity is directly proportional to K and inversely proportional to rho C. What happens when these two material have the same K, same thermal conductivity? Then you have to depend on this value rho C. See, that's why this thing is been assigned and it is a term to be in direct proportional and it is inversely proportional and it is given by one name known as diffusivity. There are a lot of diffusivity. Momentum diffusivity also you can take, how much fast the momentum is traveling. Here in our heat transfer subject, we need thermal diffusivity. Diffusivity is nothing but if you drop a ink in your t-shirt, how fast it will spread. That is termed to be diffusivity. We need to know how quickly it will spread. If you drop honey, it won't spread like that's. If you drop a ink, how fast it will spread, it's related to diffusivity. And thermal diffusivity is nowhere related with shape or size. Please take this point. Shape or size is not a concern. And here thermal diffusivity is defined by alpha. And you can see this gives an information that which body gets rapidly heated first. And it also has a strong significance in unsteady state because here only the temperature is getting changed with time. We have been seen in part 3 the steady and unsteady. Steady, no problem. Everywhere the temperature is same at any time. Unsteady, the temperature is not same. It is been changing with respect to time. This thing is telling us that how fast the body will be getting heated. In unsteady state also, we saw that the pan is getting heated little bit and one side it is, when you off the pan, it is releasing the heat. So it has strong significance on unsteady state. And now coming to Newton's law of cooling, you can see the rate of heat, that is convection heat transfer between surface and surrounding fluid directly proportional to temperature difference in surface area. Nothing but you can see here. First you can see the diagram. Now the thing is, when the air is flowing at very fast, what happens? The air carries away every heat. That is termed to be the Newton's law of cooling in simple way. See, H is a convective heat transfer between surface and surrounding. Surface is this thing, surrounding is the air. In between those there, the heat transfer is taking place. That is termed to be H, and it is termed to be convective heat transfer coefficient. These things you already know. So whatever I given is H is a quantity of rate of heat conversion takes place over a unit area for a unit temperature difference. These things all we will be seeing here. 1 meter square 1 Kelvin H equal to Q convection. Same thing, unit area, unit temperature difference. H is represent the strength of convection heat transfer. Convection heat transfer. Here conduction not, here is convection. Please be careful. H is not a property, it's an experimental determined value which is complex in nature. See, thermal conductivity K is a property. H, it is not a property. We are determining experimentally only. What I want to say here, the equation is there, Q directly proportional to del T. Already we know this, and also for area it is also directly proportional. Larger the area, the conductivity will be more. When we are writing these two things in terms of the surface like this, when convective heat transfer coefficient takes place, this alpha will be represented by H, and simply we will not write H, right? This H stands for the convective coefficient, that is what we given here, quantity of rate of convection heat transfer, rate of convection heat transfer. This is termed to be heat transfer coefficient, that is this convection heat transfer takes place in a unit area 1 meter square for a unit temperature difference 1 Kelvin, that is H equal to Q convection. These things is termed to be Newton's law of cooling, and Newton's law of cooling is not given by Sir Newton, it is given in the name of Sir Newton due to his contribution a lot of things in science. Okay, hope so friends you understand this concept. Next thing we are going to solve all the problems regarding this. We have seen lot of concepts. These concepts only will help you for solving all those problems. Hope so you have better clarity and concepts. And next sections we'll be seeing all those problems. See, if you have any queries, you can leave in the comments or you can mail me so that I can reply you. See you in next coming videos. Thank you. If you like my videos, please subscribe to my channel.